So find partial v partial p and partial v partial q, given that q e to the 2v plus v squared p plus 2 times secant of pq equals 2. So this is from an old exam. Now, there's two things going on here. First off, there's implicit differentiation. But the other thing going on here is we're using unusual choices for symbols. So we're used to things like x, y, and z. And here, we've gone to v, p, and q. And the question is, do we do anything different because our symbols change? And the answer is no. No. Because symbols can be changed. In fact, that's sort of a big idea in mathematics. Now, one thing that we can see is we can actually read off a lot of things that are going on here by just the notation. So, for example, from here, partial v partial p, that says I want to see how does v change as p changes. So this is a derivative with respect to p. So I'm thinking of p as the thing that's changing, and I'm asking how does v change as I change p. Similarly, partial v partial q says I want to say how does v change as I change q. So this term right here, this is the derivative with respect to q. In general, if you ever have this partial notation, whatever's in your denominator, that's what you're taking the derivative with respect to. So I'm saying, okay, so v changes with respect to p and q. So what we should really be thinking of is we should say, whenever I see a v, in my mind, I'm going to think of this as v of p comma q. So I'm thinking of v as being a function of p and q. So what does that mean? Well, that means that when we see this expression, what we really think of is we think of this as q e to the 2 v, which is a function of p and q, plus v squared times p. Well, wait, no, we wouldn't think of v squared. V would become v of pq squared times p plus 2 secant of q times p. All right, got that in the wrong order, but that's okay, equals 2. And again, we don't write this all out, but when we're doing our math problem, that's what we're thinking about. That's in our mind. So we're thinking, there's our thought. And of course, we're doing calculus, so we're happy. So it's a happy thought that we have. All right, so that's how we think of this equation. Everywhere where we see a v, we really think of it as there's a function v of pq. And now, the rest of it is really straightforward. In fact, it's exactly like what happened in Calc 1. So if you think back to that, which feels like a very long time ago, but it's only about a year, we said, okay, suppose I want to take the derivative with respect to p. So I can denote that partial p. That says I'm taking derivative with respect to p. And what that means is I'm going to take the derivative of both sides with respect to p. So everywhere I see a p, I take a derivative. So I go through here. I say q. Well, no, that's a constant. See, p and q are my two, what we would call independent variables. They don't depend on anything else. Other things depend on them. So q is independent of p, so there's no relationship between what q does and what p does. And then we say, okay, so there's e to the 2v, and it's like, oh, there is no p. But remember, in our mind, v is a function of pq. So what do we get? So q is a constant from our perspective. The derivative of e to something is e to something, 2v, times the derivative of what's upstairs. Well, the derivative of 2 times v is 2, times the derivative of v with respect to p. And the derivative of v with respect to p is, do you know? Derivative of v with respect to p. That's what it is. Partial v, partial p. So when we get to a point where we're like, and then we have to take the derivative of v with respect to p, we say, okay, so we write down the notation, derivative of v with respect to p. Go to our second term, and we say, okay, it looks like there's only one p, but remember, in our mind, there's actually two. Because there's this p that's sitting here, v of pq, and then there's this p out here. So we do the product rule. So, speeding up a little bit, the derivative of v squared, well, that'll be 2v to the first times the derivative of the inside, which is the derivative of v with respect to p, and then times p, plus v squared times the derivative of p with respect to p, which is 1. And the last term, well, here it's very straightforward. Derivative of secant is secant tangent, so we get 2 secant PQ, tangent of PQ, and then times the derivative of PQ with respect to P, which is Q. Take the derivative of the right-hand side, we get 0. Now, at this point, what we do is you gather all the things with a derivative. Well, it turns out, very conveniently for us, they actually are gathered already. We factor that derivative out, so we get partial v partial p times 2q e to the 2v plus 2v times p. And now the other stuff, you move over to the other side. So equals negative of v squared plus, I'm with a q up front, 2q secant pq, tangent of pq. And to finish it off, just divide through both sides. So divide through 2q e to the 2v plus 2vp. So 2q e to the 2v plus 2v times p. And there you go. That will be partial v partial p. All right. And that's the process. All right. And partial v partial q, it's the same process. So in the interest of time, because we have so many other good things to talk about, we will not do that one. But you should try it. You should try it. It's good to practice. So what are we talking about today? Well, we want to get a good grip on how to think about things. We're getting closer. We talked about tangent planes, but we really want to talk about how do we understand tangent planes. So we should think of the analogies. So we know how to think about tangent lines. We're really good at that. So for example, if I have this function y equals f of x, and I have a point A, the tangent line would be y minus f of a equals f prime of a times x minus a. And so what we want to do is we want to say, okay, what's playing the role of f prime of a? Because now we have something going on where we have all these partial derivatives. So is there like one object, a single thing that can combine them all? And we think about, okay, we know how to find tangent planes. So that becomes z minus f of ab. That matches with the y minus f of a. But now we have these two terms, f sub x ab times x minus a plus f sub y at ab times y minus b. And here's sort of our insight, which says we can combine these together, and we can do it by the following. Write it as a vector. So we're going to write this vector of partial derivatives, f sub x ab, f sub y ab dot x minus a, y minus b. So that we can say, okay, there's this vector here. We're going to call it a name. We're going to call it upside down triangle, FAB. Actually, we don't call it upside down triangle. We're going to give it a better name than that. But for right now, that's the symbol. And so whatever this is, it's analogous. See, it's like f prime of a, that matches with this vector. Then the x minus a, that matches with this new vector, which really is talking about changes. So we say, okay, so that's going to be our derivative. When we think about the derivative, what's acting like the derivative? The answer is this vector. So what is that vector? Well, it's called the gradient vector. And so it consists of all the partial derivatives. So it's actually very simple to find. If I have a function and I want to find the gradient, I just go through and say, let me find all the partial derivatives. And then we're good to go. And gradients, of course, this is for functions of two variables, x's and y. But you can find gradients for a function for any number of variables. The key is it's a vector, and each entry corresponds to a partial derivative. So I have a function, g of x, y, z. Well, then I'm going to have three slots. Derivative of g with respect to x, derivative of g with respect to y, and the derivative of g with respect to z. All right. Now, what's this upside down triangle? Well, the way we should think about the upside down triangle is that it's a collection of partial derivatives. So the first entry stands for take the derivative with respect to x. The second entry says take the derivative with respect to y. And the third entry says take the derivative with respect to z. And we're going to have like a whole class where we go through and we talk about all the various things that we can do with this thing. Now, notationally, it has a name. This is called del, or sometimes it's called nabla. Does anybody know nabla? Do you recognize that? It's the idea for nabla is it comes from a Greek harp. So if you look at a Greek harp, what it looks like is it's a little triangle, and then there's little strings. And so you'd play the Greek harp. And so the idea is that this somehow gives us information about various harmonics and various things. But that's for other classes to go into. All right. And of course, this gives you an example where you can think of the gradient as saying, the gradient of f is like, well, I'm scaling this partial derivative by f, and so you have what goes on here. So, okay, so scaling. All right. Now, the nice thing about the gradient is it has a lot of the beautiful properties that we would expect to be true. So if I want to take the gradient, say, of f plus g, that's the gradient of f plus the gradient of g. If I want to take the gradient of some constant times f, I can pull out the constant. Or maybe I want to take the gradient of two functions multiplying together. Well, if you work it out, you have a product rule. That's f gradient of g plus gradient of f times g. And the reason that you have all of these rules, and the reason that this all works, is because it works entry-wise. And we know that vectors work really well entry-wise. And when we're taking derivatives, we go entry-wise, and then we can do manipulation. Vectors work really well with addition and scaling. And at the end of the day, that's what derivatives boil down to. Addition and scaling, and then the idea of I can get close. And so vectors really mix well. So the important thing is that what you would expect to be true for something that acts like a derivative is still true. So that's good news for us. All right, well, time to practice. And so we're going to do a lot of practice here. Many examples. Any questions before we jump into examples? Okay. Good. Then we are ready. So, here we go. Find the gradient of f for f of xy equals sine of xy plus x cubed plus xy. All right. Well, that shouldn't be too bad. We say, okay, gradient of f, that would be the vector which has my partial derivative. So f sub x, comma, f sub y. All right. No big surprise there. So let's take our derivatives. Good practice to take partial derivatives. What's the derivative with respect to x? Derivative of sine of xy. Y cosine of xy. That's right. The derivative of x cubed, and again with respect to x. Minus 3x squared. That's good. The derivative of x times y with respect to x. Why? Well, I'm asking the question because we need to know. Oh, wait, no. Of course, you meant the variable y. Yes, y, comma. Okay, so there's the derivative with respect to x. What's the derivative with respect to x? What's the derivative with respect to y? What do we get? X cosine of xy. Derivative of x cubed with respect to y? 0, because x and y are independent of each other. So whatever y does, x has no effect, and vice versa. Derivative of x times y with respect to y? X. And there you go. All right. Now I can already see you thinking, I hope we have a question about let's find the gradient. Well, I can promise you, you'll definitely have a question where you need to find the gradient because it's a cool tool. Who knows if it's just that. All right. Now let's do something where we have three variables. Find gradient of g. G of x, y, z equals x squared z plus log 1 plus z squared. All right, so let's start going. Gradient of g will be, what's the first entry? Okay, so there's only one x, so the first entry will be 2xz. What's the second entry? 0. Now, should we put 0 in? Yes, we should. It's absolutely appropriate for us to put a 0 because we should have every partial derivative accounted for. So sometimes you might say, well, this function isn't varying with that variable, but we need to keep track of that information. So even if entry is 0, we still put it in. What's the last thing going to be? Derivative with respect to z. Okay, derivative of x squared times z with respect to z is x squared. How about the last part, log of 1 plus z squared? Yeah, 1 plus z squared goes downstairs because the derivative of log of anything is 1 over the inside, then times the derivative of the inside, and since the derivative is with respect to z, that's a 2z. So again, the first entry, this is the partial g partial x. The second entry, partial g partial y. The last entry is partial g partial z. All right, well, we're doing pretty well. Let's go to our next example. Find the gradient of h for h of z u p equals z squared u plus sine of p e to the u plus zp squared. Now you might be wondering, why are you using strange letters here? Well, a couple things, just to show you might encounter strange letters, but also because this gives me an excuse to say, huzzah up! Right? Yeah. Okay, good. So, well, all right, I took my chance. All right. So there we go. We have this expression. Now, previously we said, okay, it was pretty clear what order we should take derivatives, you know. Derivative with respect to x, derivative with respect to y, derivative with respect to z. When I'm finding the gradient here, what's the right order to take the derivatives with respect to? Z then u then p. Now, how do we know that's the right order? Yeah, you see, these are all just sort of placeholders. So really, you should think of the z as saying the variable in the first slot. U is that variable in the second slot. And p is the variable in the third slot. And so when we fill in that gradient, it's, well, what goes in the first slot? That's the first part. What goes in the second slot? That's the second part. And what goes in the third slot? That's the third part. All right. Well, that's actually the hard part of this one. So let's do the easy part. So what's the derivative with respect to z? 2z times u. Anything else? Plus p squared. Okay, good. All right, derivative with respect to u. That's our next slot. Z squared plus sine of p e to the u plus 0, right? Okay, good. Last slot, derivative with respect to p. We get cosine p e to the u and 2 times z times p. And there we go. All right, good. This one's feeling a little lonely. Didn't get boxed, so I'll box it now. All right. Now, those are my examples. Now you get to pick. All right, find the gradient of g of x, y, z, where g of x, y, z is, well, what function do you want?
Arctangent of x, y, z.
Okay, that's a function, that's true. Anything else?
2.
2. Okay.
Throw a g in there now, or do you want it as x?
Well, we're going to have it as x, y, z. Now we can throw other symbols in. We could throw a t here, but if I put a t here and I take the derivative, what's going to happen? It's going to be a constant. So if I have other symbols, you know, like for example, those poor Calc 1 students, we put an e cubed on the test, and they took the derivative of e cubed. You'll never guess what they wrote down. Oh yeah, you guessed. Okay, it was e cubed. You know, because they're like, it's a letter. I better, you know, it's a variable. You know, not everything that's a letter has to be a variable. So, okay, well, you're going to make it easy on me. All right. Anything else? No? Okay. Okay, all right. So in this case, those are all going to be straightforward. You're going to get yz over 1 plus xyz squared, and then comma, you're going to get xz over 1 plus xyz squared, and then you're going to get xy over 1 plus xyz squared. All right. Well, I mean, it's true. Okay, good. Now, we have a gradient, and we want to start asking some other questions, and we'll come back to the gradient in a little bit. But let's go back to our partial derivatives. So how do we think of our partial derivatives? So we have this partial f, partial x, and partial f, partial y. So when I have those values, and when I'm taking a value, I mean, I'm at a particular point, and I evaluate the partial derivative, I get a number. What's that number? The answer is that we can think of it, it's how the function changes, say, in the x direction, if I'm taking the derivative with respect to x, or if I'm taking the derivative with respect to y, it's how the function changes in the y direction. More explicitly, it's in the positive x direction or in the positive y direction. So what I can think of happening is I could say, okay, you can imagine that you're in three-dimensional space. So imagine that was a three-dimensional space. And then downstairs, here's our domain. All right. So there we are. And this is way more complicated than it needs to be, but okay. And up here, of course, is our surface in three-dimensional space. And now, the question is, suppose I'm here. So, when I'm talking about partial f, partial x, that says, what's happening as I move in that direction? So, the positive x direction. So, partial f, partial x says, how am I changing in that way? So, if I were to just move in positive increasing x, what's my rate of change? So, in other words, I'm looking at, how does it go upstairs on the surface? What's happening? If I want to know partial f, partial y, that says, okay, suppose in the downstairs I'm moving this way. So here, I want to understand what is partial f, partial y. So maybe on the surface, maybe I'm moving that way. So the partial derivatives give me information about how I change in two directions. Now I'm emphasizing the word two directions because how many directions are there? Infinitely many. Infinitely many. Because I can go lots of different ways. All right. So the question becomes, okay, how do we handle other directions? And the answer is, we're going to do something called directional derivatives. So for right now, I'm going to let P be the point. So in terms of the picture, this point right there, that's P. So there's my P. So here we go. Partial f, partial x. Let's write down what these are. How do we do this? So this goes back to how we did partial derivatives. So that's the limit f of x plus h comma y minus f of xy over h. Now I can think of f of x plus h as I start from my point P and I go a little bit in the I direction. Now remember, I is the positive x. It's the vector that points in the positive x direction. So I can think of it as like, oh, I'm perturbing my point P by a little bit in the x direction. If I do partial f, partial y, we have that limit definition. And I can think of it, oh, this x of y plus h, it's like I took my point P and I perturbed it a little bit in the positive y direction. So h times j. So that tells us, how do we do directional derivatives? Well, the answer is we do it this way. We're going to take a limit as h goes to 0 of f of p plus hu minus f of p over h. So how do you interpret that? Well, if you think about it in terms of your input, so let me put this picture back up here. So here's my inputs, my x, y plane. Here's my point P. So if I want to take my derivative in a particular direction, let's say I want to go off in this direction here. So if that's my direction, Well, the way we think about direction is we think about direction as a unit vector. So here, this is u equals unit vector. That's pointing in the direction I want to go. And what I do is I do the following. I say, all right, I'm just going to go just a little tiny bit, just enough. So this is h times u. And so this point here will be p plus hu. So now what I'm going to do is I'm going to say, well, let me compare the function where I've moved just a little bit minus the function at my original point divided by how far apart I am. All right? That's the idea. Now, you're probably like, ugh, well, how do we do all this? So the capital D, by the way, stands for directional derivative. The U stands for a unit vector. The F, what's the function? And P, what's the location? So that's what all of our notation means. So we're going to do an example. All right. Find the directional derivative in the direction cosine theta, sine theta. You'll notice that cosine theta, sine theta, what is that? Well, this is, if we think about it at being 0, 0, cosine theta, sine theta is the point on the unit circle where we've gone up by an angle theta. So that's our vector. So find the directional derivative of this function, square root of absolute value times absolute value of x times absolute value of y in the direction cosine theta, sine theta. Do you remember this surface? The square root of absolute value of x times absolute value of y? It's the one that was pinched, where it was sort of, I can't draw this. Okay, go back into your notes. It's in there. It kind of had that sort of Sydney Opera House vibe going for it. But it's the one where it's not very smooth at the origin. But that's okay. We can still try and see what happens when we apply the definition. So what's the definition? Well, we're going to take the limit as h goes to 0 from above of f of p plus hu minus f of p all over h. Because that's what the definition says to do. So I'm going to use the definition. Now, my point P, that's at 0, 0. So P is 0, 0. So what do I have? Well, this is the limit as h approaches 0 from above of f. And so I'm going to take P, which is 0, 0, and then I'm going to add h times cosine theta, h times sine theta. So the point becomes h cosine theta, h sine theta, okay, minus f at 0, 0, all over h. So, good news, we can take and evaluate now. So f of 0, 0 is going to go away. That's 0, because square root of 0 times 0 is 0. Then we have the square root of h cosine theta, h sine theta, all over h. Now, the good news is, on the inside, what do we have? H squared. And square root of h squared, what does that become? It becomes h. Now, normally when we say square root of h squared, what would we say? The absolute value of h. But what do we have going for us? Yeah, there's that plus symbol, which says I'm always approaching from one side. So I want to differentiate, going in one direction versus going in the exact opposite direction. So what happens is the h's all cancel, and now, well, this limit doesn't depend on h at all. And therefore, we say, aha, I can find the rate of change in any direction. It's the square root of, whoops, and I forgot absolute values here. Should have put those in. Square root of absolute value cosine theta times sine theta. All right, so there we go. So we can take directional derivatives, even if our surface doesn't have a nice smooth point. We can still take directional derivatives. Now, we go back to Calc 1 and say, well, sure, we could take directional derivatives with limits, but we don't want to. So what do we want to do? Well, we want to get rid of the limits. That was our big thing in Calc 1. It's like, get rid of all the limits. We don't want any more limits. So that's what we're going to talk about next. How can we do directional derivatives without limits? Okay, so here we go. Let's find out. Well, no surprise. When a function is differentiable, that means it's locally smooth. But really, it means it's easy to work with. So let's see what happens. So we know that f of xy minus f of ab is approximately partial f partial x at ab times x minus a plus partial f partial y at ab times y minus b. All right, so that's what it means to be differentiable. And really, the differentiable comes down to saying that this approximation is good. That's what differentiable means. Because you could always say, well, sure, any function can be written like this. It just might be that this is a terrible thing. But differentiable means that's a good approximation when a and b are x and y are close to ab. Okay, so here we go. Let's just put our notation together. Our point is going to be ab. Our vector, that's a unit vector, that's st. So that our point p plus h times our unit vector, well, that means I'm going to perturb. I'm going to take a, and then I'm going to move h times s in the, so that's the x direction, so a plus hs, and then b plus h times t. That gives me my y coordinate. So let's find out what happens. So f of p plus hu minus f of p. Well, what do we get? Well, we just come up here and we say, all right, well, what happens? We still have the partial f partial x ab, partial f partial y at ab. Those are the same. But now, look at what the entries become. X minus a. Well, why does it become h times s? Well, it's a plus hs minus a. So that's where the hs comes from. This ht, b plus ht minus b. Now, if we stare at that, we say, hey, that looks a little familiar. That looks like what we were doing a little while back. We can pull out an h. That's common. And then we say, oh, that looks like the partial derivatives dotted with st. Which means we get h times our gradient at our point dotted with u. Now we're ready to go. So, remember what happens when we're taking our directional derivative. Well, we're taking the limit as h goes to 0 from above, f of p plus hu minus f of p all over h. Well, if I divide both sides by h, I see that f of p plus hu minus f of p is approximately times the gradient of f of p dot u. But remember the approximation. It gets better the closer we get. And as h goes to 0, we're getting closer. So that our approximation becomes equality. Which means that directional derivatives are nice. They're simple. It comes down to the gradient. You find the gradient, dot it with the direction that we need to go. And there you go. That's how you find directional derivatives. Good. Well, that doesn't sound so bad. Let's try some examples. All right. So when we're doing a directional derivative, now this is the formula. We're not going to think about the limit anymore. Don't use a limit definition to take a directional derivative. Take the gradient at the point dot u. That's what you need to remember. So find the directional derivative of the following. F of xy is x squared plus 3x minus 5y squared plus 7y plus 11, pointing in the direction 3, negative 4 at the point 1, 1. So we need to put some things together. So what do we need? Well, the two things we need are the gradient and u. Let's talk for a second about u. Do we have our vector u? Well, is this u? It's kind of close, right? Because it is the direction. What's wrong with this vector? It's not a unit vector. So remember here that this u has to be a unit vector. So what we'll do is we'll say, well, that's the right direction. Let's just make it a unit vector. So how do I transform that vector into a unit vector? I find its magnitude, divide out. So what's the magnitude of 3 comma negative 4? Well, someone is faster than me, so I'm going to go slow. Square root of 3 squared plus negative 4 squared, which is square root of 9 plus 16, which is square root of 25, which is 5. All right, so our unit vector will be 1/5, 3, negative 4. I can multiply the 1/5 through, but it's just as easy for me just to write it in that form. 1/5 times 3, negative 4. Okay, what's the next ingredient that we need? We need the gradient. All right, well, so let's find that. So let's start by just finding the gradient. What is the gradient of f? Okay, so taking the derivative first with respect to x, 2x plus 3. Anything else with respect to x? No. Comma. Now with respect to y. Okay, there's a y, negative 10y, and plus 7. Okay, so 2x plus 3, negative 10y plus 7. Now, what's the next thing we need to do with this gradient? Plug in the point, right? Because it's not just a gradient, it's a gradient at a point. Because when we're talking about directional derivative, the final answer should not have x's and y's in it. It should have a number. Because it's saying, what's the rate of change in this direction? I'm looking for a number out. All right, so our point, well, that's the point 1, 1. So we're going to plug in gradient of f at the point 1, 1. What do we get? Well, 2 plus 3, 5. Negative 10 plus 7, negative 3. So, last thing is we take the dot product. So, the directional derivative, du f at p, is 5 comma negative 3 dotted with 1/5, 3, negative 4. Well, okay, the 1/5 can come out. Now we get to remember dot product. How do we take 5, negative 3 dot 3, negative 4? Well, that's the multiply the coordinate entries. 5 times 3, 15. Negative 3 times negative 4, positive 12. And then what we're going to do is we're going to add all these together. Well, all of them being 2. And so we get 15 plus 12, which is 27 over 5. And so that means that at the point 1, 1, for this function, if we move in that direction, 3, negative 4, our rate of change is 27/5. All right, that's not so bad. So let's try a few more examples. We have some time. We can get some more examples in. Now, we talked about 2 variables. The same thing holds for any number of variables. So we can do 3 variables. You can do 18 variables. We'll probably only stick to 2 or 3, but the same process works for any number. So here we go. Suppose you have this function, g of x, y, z is xz plus 5y squared minus 6z plus yz plus 31. And it says, find the rate of change of g at the point 1, 1, 1 in the direction of the point 3, 0, negative 1. Now, let's work our way through the process. So what's the process? Well, you got to think about finding the gradient and finding the unit vector. That's the process. Find those 2 pieces, then dot them together. Let's start with our unit vector. Do we have our unit vector yet? No. In fact, we don't even have any vector at all. Not yet. But we were told how to make a vector. Because it says, suppose you start at this point. So here's the point we're at, and we want to go to another point. And I don't know, let's say this is the other point, 3, 0, negative 1. It's probably not there, but all right. It doesn't have to be right to help us get the right intuition. So what's the vector? Well, we want the vector that's pointing from 1, 1, 1 to 3, 0, negative 1. But we want it to be a unit vector. Well, first off, let's not worry about the unit part. Let's just find a vector that points in the right direction. So what's a vector that's pointing in the right direction? 2, negative 1, negative 2. Which is, if I start at 1, 1, 1, how much do I have to change to get to 3, 0, 1? Well, the x I need to change by 2. The y I need to go down by 1, so that's negative 1. And the z I need to go down by 2, so negative 2. Now, is this our unit vector? No, but at least it's a vector. That's progress. What do we do next? Find the magnitude of that vector, because with the magnitude, we can make it a unit vector. So we get 2 squared, which is 4. Negative 1 squared is 1. Negative 2 squared is 4. Square root of 4 plus 1 plus 4, well, that's the square root of 9, or 3. Suspiciously nice. You should also think that, wow, a lot of these problems are suspiciously nice. And if they're not being suspiciously nice, check your work. Check your work. Okay, so our u that we're going to use is 1/3 times 2, negative 1, negative 2. Okay, so there's our sort of our first half. We found u. What's next? Find the gradient. Okay, so what is the gradient of g? Well, take derivative with respect to x. I see an x there. So derivative of x times z with respect to x is z. And no, there's no x. That's not an x. No x is there. Oh, that's okay. There's the first entry, comma. Second entry, now with respect to y. There's no y. Well, there's a y. Derivative of 5y squared with respect to y, 10y. No y on that term. Oh, there's a y. Derivative of y times z with respect to y is plus z. Yep, good. And, okay, no y on the last term. All right, comma. Now with respect to z. Derivative of x times z with respect to z, x. No y there. Sorry, no z there. Derivative of negative 6z, negative 6. Derivative of y times z, y. Okay, so there's our gradient of g. What do we do with our gradient? Evaluate it at which point? Yeah, see, it tells us at 1, 1, 1. See, it's the temptation, there's like 2 points. But we have to remember, one point is telling us where we're at, the other point is giving us our direction. So we're at 1, 1, 1. And the nice thing about 1, 1, 1 is it's easy to evaluate when you have ones. So you end up with 1, then you get 10 times 1 plus 1, which is 11. Then you get 1 minus 6 plus 1, which is negative 4. So, we're almost done. We take 1, 11, negative 4, the gradient, dot, our unit vector, 1/3, 2, negative 1, negative 2. So, this is our duf at p. This will become 1/3, 1 times 2 is 2. 11 times negative 1 is minus 11. Negative 4 times negative 2 is plus 8. 2 minus 11 plus 8? Yes, negative 1. Negative 1/3. Is it okay that we got a negative answer out? Absolutely. Derivatives can definitely be negative. It just means that if we move in this direction, our value is going down. So if we think of it maybe like G represents something like temperature, as we start moving, our temperature, it's getting colder, perhaps. All right, last example for today. So let f of xy be a differentiable function. Okay, so we don't know what f is, but we know it's a differentiable function. Given that at the point 1, 1, the directional derivative towards the point 4, 5 is 8, and that the directional derivative towards the point negative 3, 4 is 1, find fx at 1, 1 and fy at 1, 1. So we're given information about 2 directions, and then we want to use that to figure out other information. In essence, what we have is we have the directional derivative for 2 different directions, and we want to find the directional derivative for the x direction and the y direction. All right, now the problem here is we don't know what f is. But that doesn't stop us. It hasn't ever stopped us before. So let's think about what we know. So we're at 1, 1, and we're taking a directional derivative towards 4, 5. Well, okay, so from 1, 1 towards the point 4, 5, what's our vector? The vector would be 3, 4. Now, That's not a unit vector. So if we make it a unit vector, what would we do? 1/5. So this would be our vector u. So the directional derivative towards 0.45 is 8. So we could say, aha. So here we would say that the directional derivative is 8. So 8 equals what? Well, this is our du. Well, that's 1/5, 3, 4, f at the point 1, 1. So according to the formula, that equals the gradient. Oh, where's the formula? It's on the other page. The formula says you put in the gradient of f dot u. Okay, so what's the gradient of f? Gradient of f at 1, 1 is equal to, what's the answer? Well, the gradient of f consists of what? Partial derivatives. So the first entry is a partial derivative with respect to x, and then what do? You plug in 1, 1. What's the second entry? Fy at 1, 1. So there's our gradient of f at 1, 1. All right, so what we're going to get is it's the gradient fx at 1, 1, comma fy at 1, 1. And actually this is good news for us because notice that's what we're looking for. So it's actually really useful that that turns out to be what's inside there, dotted with 1/5, 3, 4. Now we can move the 5 across, and so we can write this as 40. So I multiplied both sides by 5 is equal to 3 fx at 1, 1 plus 4 fy at 1, 1. All right, so that's one fact we know. But do we know anything else? Yeah, there's a second directional derivative. So we have to get that fact. So we have 1, 1 towards the point, -3, 4. Well, what's the vector? 1 to -3, what do I change by? 1 to -3, I change by -4. 1 to 4, I change by +3. So that's the vector that goes between those 2 points. To make it a unit vector, what do? Multiply by 1/5. And so now we have that directional derivative is 1. So we get that 1 is equal to the directional derivative in the direction 1/5, -4, 3, f at 1, 1. Well, that would be, again, fx at 1, 1, fy at 1, 1, dotted with 1/5, -4, 3. Multiply both sides by 5. We can conclude that 5 is equal to -4 fx at 1, 1 plus 3 fy at 1, 1. So what are we down to? Yeah, our favorite bread and butter. It's like, this is why I take calculus. So I can have 2 equations and 2 unknowns. That's what wakes me up in the morning and gets me going. All right, well, let's see if we can't do this really quickly. Okay, so 3 fx 1, 1 plus 4 fy at 1, 1 equals 40, and minus 4 fx at 1, 1 plus 3 fy at 1, 1 equals 5. And now what can you do? Well, just multiply things together. So for example, if you multiply that by 4, multiply that by 3, you'll get 12 fx at 1, 1 plus 16 fy at 1, 1 equals 160, and negative 12 fx at 1, 1 plus 9 fy at 1, 1 is equal to 15. And you might say, well, why did you choose 4 and 3? Well, notice what's going to happen to the fx's if we combine now. They're going to cancel off. So 25 times fy at 1, 1 equals 175. So now divide both sides by 25. What is f sub y at 1, 1? It's 7. And once you know that, go back into your favorite equation. Let's say the first one. We get that 3 fx at 1, 1 plus 4 times 7, which is 28, equals 40. Well, subtract 28 from both sides, divide both sides by 4, and now you have your other term. And there's the answer. And you're done. And we're done, and we'll continue next time.